In everyday life, we see some objects at rest and other in motion. Birds fly, fish swims, blood flows through the veins and arteries, and car moves. Atoms, molecules, planets, stars, and galaxies are all in motion. We often perceive an object to be in motion when its position changes with time. Therefore, we can say motion is the change in the position of a body with respect to time. However, there are situations where the motion is inferred through indirect evidence. For example, we can infer the motion of the hair by observing the movement of dust and the movement of leaves, movement of branches of trees. What causes the phenomena of the sunrise and sunsets and changing of seasons? Is it due to the motion of the earth? And if it is true, why don't we perceive the motion of the earth about its axis? We all know that earth move about its axis, right? We said it move about its axis and it revolve around the sun in a circular path or an elliptical path, right? Now, why don't we humans that we are living on earth perceiving the rotation or the motion of the earth itself, if this is actually true? Now, an object may actually appear to be moving from one person and be stationary for the other person. Let us take for an example a car that has a passenger. Let us say this is a car and it has inside it passengers as well as the driver having to drive the car. And outside of the car, we have humans staying by the roadside. And also we have trees by the roadside or as well. We have trees by the roadside. You know, the passengers that are inside the moving bus are seeing the roadside trees as well as the people that are standing by the roadside. They are perceiving them to be moving backward, and this is because they are moving forward, right? And those people that are outside, which means the roadside, the roadside people perceives those people that are inside the car to be moving forward. So the passenger are perceiving people outside to be moving backward. The roadside people are perceiving people inside the car to be moving forward. But those that are inside the car perceives the driver as well as other passengers to be stationary, right? Now, what do these observations indicate? It indicates that an object may appear to be moving for one person and it will appear to be stationary for the other. An object may appear to be moving forward for one person and will be moving backward for the other. Most motions are complex like that, and some objects may move in a straight line like this one that I just mentioned now. Others may take a circular path, like the motion of the earth about its axis, and there may be a situation where we have the combination of moving in a straight path and moving in a circular path, just like the tire of these cars. The tire is moving circularly and it's also moving in a straight path, moving the car forward. In this chapter, in this video, we are going to learn and describe the motion of an object along the straight line, and we shall also learn and express such motion through simple equations and graph, and later we'll be describing the circular motion. So let us get into today's class. Now, we describe the location of an object by specifying a reference point. Let us understand it by example. Let us take for an example. There is a church. There is a church, and the church is at the north of a railway station. So this is a railway station and this is a church. A church is at the north of a railway station. Now, if you want to specify the position of the church with reference to the position of the railway station, therefore we are going to say the railway station is our reference point. The railway station is our what? Is our reference point, right? And we could have chosen other reference points. For example, there is another kiosk at this place. Let me say there is a kiosk here, and we want to specify the position of the school with respect to the position of this kiosk. Therefore, we can say the kiosk is the reference point. The church can also be the reference point in this case if we are trying to specify the location of the railway station with respect to the church. Therefore, our church is the what? The reference point. So we can choose different reference points. Now, therefore, we have to describe the position of an object. And if we want to describe the position of an object, we have to specify a reference point. And this reference point is termed origin. Are you getting me now? Now, the simplest form or the simplest type of motion is a motion along a straight line. And let us learn about the motion along a straight line first. Let us consider the motion of an object or the motion of a body moving in a straight line. Let us say the motion of the body moving in a straight line, and the length of this line from point O, which is the origin, to point A, which is where it is right now. It is from 0 meter to 60 meter. Now, as the body is moving forward, it reaches point C, which is 25 meter, reaches point B, which is 35 meter. So this is point C and this is point B. So we have A, B, and C with O, which is the origin. That is our origin. Now let us now take for an example. It moves from O to B, right? We now want to calculate the distance at which it moves. We are going to say the distance equals to 35 plus 0, which is equals to, which means it has moved 35 meter distance, right? Now let us now take for an example. It's now moved from point 0, which is point origin, to 60. Would have said it moves 60 meter. That's the total distance covered. Now let us now see it's now moved back from point 60 to point 35 rather, which means from point A to point B. They now ask you, what is the total distance covered in this case? What is total distance covered? You see the total distance covered, let me use that one as S, equals to the distance covered when it moved first, which is 60, plus the total distance covered when it moved backward, which is 35, and that's equals to 95. Now, that is the concept of distance. Are you getting me now? Now, from this example, we can also find out the distance of the final position, C, and all like that. What is now displacement? We have mentioned distance. Displacement is the shortest distance measured from an initial to the final position of an object. I said is the shortest distance that is measured from an initial to the final position of an object. In my own words, I can say it is the change in the distance measured from the initial to the final. So I can say my displacement equals to in final minus initial, or initial minus final in some cases, initial minus final. Now, let us now take for an example. We have calculated the total distance covered by this one. Let us now calculate the displacement. You know, when it is going forth, this is our initial, then it reaches this place, which means this is our what? This is our final. But when it wants to go backward, this final changes to initial, and this 35, which is point B, changes to final. Which means if we want to calculate the displacement in this case, we just say what? We just say that is 60. That's going to be 60 minus 35, and that's equals to 25 meter. So that is the displacement. So in this case, we are going to see that distance is not always equals to displacement in every case. Even in this case, if we are trying to calculate displacement, at this being it goes back to its origin. We find out that the displacement will be equals to 0. Right? So if we are asked the question, an object moved through a distance, can it have 0 displacement? Yes, it can have 0 displacement. That is if it moves back to its original position, move back from one place, so from one end to the other end, then returns back to its origin, then it can have a 0 displacement. And if they ask you to use an example to support your answer, then you can use this particular example. And that is the concept of speed and distance. What is now the application of speed and distance itself? That is where distance and displacement itself. Don't mind me. Now, that is where we are going to the concept of speed and velocity. What is speed? Different objects, you have to understand that different objects may take different amount of time to cover a given distance. Some of them may move fast, some may move slow, and the rate at which objects move can be different. Also, the rate at which different objects move can be the same in some cases. One of the way of now measuring the rate of a motion to find out the distance that which an object travel is speed. Speed is a scalar quantity. Speed is a what? Is a scalar quantity. And when they say something is a scalar quantity, it means it has magnitude or value, but no direction. It has a magnitude or value, but no direction. That is what a scalar quantity is, which means in speed, we are specifying the magnitude of a body without specifying the direction at which it moves. It requires only magnitude without direction. So we can say we can also calculate an average speed. And what is an average speed? An average speed equals to the total distance traveled divided by the time taken. The total distance traveled divided by the what? Divided by the time taken. Now, let us take for an example. Let us say our first example, an object travels 60 meter in 4 seconds. Then another 60 meter in 2 seconds. What is the average speed? This is actually very, very easy. What you're just going to say is that the average speed equals to the total distance traveled equals to 16 plus 16, because total means sum, right? And the time at which is moved them equals to what? Equals to 4 plus 2, and that's equals to 32 divided by 4. What is 32 divided by 4? If you press your calculator, as I'm pressing it here, I'm going to have 5.33 meters per second. That is what we have. So the unit of speed is in meters per seconds. That is the unit of speed. Now we have discussed the concept of speed now. What about speed with direction? Speed with direction. You see, the rate of motion of an object can be much more comprehensive if we try to specify the direction. And remember, I've already said displacement deals with direction. I've already mentioned that. So we can say the quantity that specify both distance at which an object moves and the direction at which it moves is termed velocity. So let us say this is a school and this is a principal office, and we have a student here. The principal office, let us say, according to, let me say, cardinal point, we have north, we have east, we have south, and we have west. So this particular principal office is at northeast. So a particular student is moving at a speed of 10 meters per second towards the principal office, which is northeast. Or let me say it moved a distance of 10 meter towards what? Towards the principal office, which is northeast. So can you see that in this case, I have specified the distance at which he is moving and the direction at which he is moving, and that is the concept of velocity. And velocity, mathematically, velocity is the rate of change of displacement with respect to time. Rate of change of displacement. So velocity equals to change in displacement over time. So velocity is the final displacement minus initial displacement divided by the time taken. But we also have something we call average velocity. Average velocity is now equals to initial velocity plus final velocity divided by 2. And we'll be using this particular equation in the equation of motion, which is to come later. So whenever you see u, it means initial velocity. Whenever you see V, it means final. So let me indicate that. Initial velocity for U, final velocity for V. So velocity is the change in placement over time, and um, average velocity is the sum of the initial and the final velocity divided by 2. Let us now take another example. They said a speedometer read the speedometer of a car reads 2,000 kilometers at the start of the journey and 2,400 at the end of the trip. If the trip took 8 hours, calculate the average speed in kilometer per hour as well as in meters per second. This is actually very, very easy. What we're just going to do is we want to calculate the average speed, right, in kilometer per hour and meter per second. So our average speed will now be equals to, what are we going to do? The final distance subtracted from the initial distance divided by, the initial distance is 2,000 divided by 2. And that will give us what? Divided by the time taken, which is 8 rather. 8. And 400 divided by 200, 2,400 divided by 4,000 equals to 400. Divide everything by 8, and you're going to be having 50 kilometer per hour, right? Now, how do we convert to meters per second? That's actually quite easy. You know, we have 50 kilometer per hour, and we know that 1,000 meter make 1 kilometer, and we know that 60 seconds make 1 minute, and 60 minutes make 1 hour. So that will give us what? That will give us 50 multiplied by 1,000 divided by 3,600. And if you should divide them, you're going to be having 500 divided by 30, and that will be giving us what? That will be giving us sum of 13.9 meters per second. So it is moving at 50 kilometers per hour and 13.9 meters per second. That is the rate at which it's moving. Let us take for another example. They say Usher swims in a 90-meter long pool. She covers 180 meters in 1 minute by swimming from one end to the other back along the same straight path. So I want you to take this particular statement, straight path. Find the average speed and the average velocity of Usher. What are we going to do? Average speed. Let me see. U average equals to the total distance covered. That is, total distance covered equals to 180 meters divided by the seconds at which it's covered. That's 1 minute, which is 60 seconds. And 180 divided by 60 give us what? Give us 3 meters per second. Now, what is now the average velocity? Average velocity. We know that average velocity equals to displacement over what? Displacement over time taken. Displacement divided by time taken. Right? Now, remember that we have already mentioned in the example that we cite in the first stuff that we have, that if something starts at a particular origin and end in a final, then go back along, the displacement equals to 0. So in this case, we have to understand that in this case, the swimming pool is 90 meter, right? 90 meter. So the lady swims 90 meter to the front, then 90 meter to the back. Therefore, the change in displacement equals to, so the velocity equals to 90 minus 90, everything divided by 60. And that's equals to 0 divided by 60. And our final velocity, or the average velocity, equals to 0 meters per second. So you can see that in this case, the average speed is not equals to the average velocity. So the average speed is 10 meters per second, and the average velocity equals to 0 meters per second. Now let us talk about rates of change of velocity. What is the rate of change of velocity? That is referred to as acceleration. During uniform motion of an object along a straight line, the velocity remains constant with time. In this case, the velocity of an object at any time interval is 0. However, in non-uniform motion, velocity varies with time. It has different values at different instants and at different points along a certain path. Thus, the change in the velocity of the body during time interval is not 0. So we can express the change of a velocity in a concept we know as acceleration. So we have another physical quantity. We termed it acceleration. And what is acceleration? Acceleration equals to change in velocity divided by time taken, or rate of change of velocity. Change in velocity divided by time taken. And remember that I told you that velocity, we have initial velocity and final velocity. And we know whenever you hear change equals to final minus initial. So that is acceleration equals to final velocity minus initial velocity divided by time taken. And that is what we have there. Now let us take an example. They said, starting from a stationary position, Raul paddles a bicycle to attain a velocity of 6 meters per second in 30 seconds. Then he applies a brake such that the velocity of the bicycle comes down to 4 meters per second. In the next 5 seconds, calculate the acceleration of the bicycle. Quite easy. Now, let us take this particular example. They said um, it moved from a stationary position, right? Which means in a stationary position, the initial velocity equals to 0 and the final velocity equals to 6 meters per second, right? And the time at which it moves it is 30 seconds. So in the first instance, our acceleration equals to 6 minus 0 divided by 30. 6 minus 0 divided by 30 will give us what? Will give us 1 over 5, and that is equals to 0.2 meters per second. That's our acceleration. Are you getting me now? Now, how about in the second instance? The first instance is when it moves at 30 seconds. The second instance is in 5 seconds. So in second instance, it now moves from what? In second instance, our initial velocity will now be equals to what? Will now be equals to 6 meters per second. And our final velocity will be equals to, it moves to 4 meters per second. Therefore, our time equals to 5. Therefore, we can say what? We can say that our acceleration equals to 4 minus 6 divided by 5. And that's equals to 2 upon 5. And that will give us minus 0.4 meters per second. Why is it minus 0.4 meters per second? It's because a brake was applied. Now, we can represent this in a graphical representation. In a what? In a graphical representation. See, we said, let us say this is velocity, this is velocity, this is velocity, and this is time, right? Now, in this case, let me just make it a little bit smaller so that you can see what I'm doing. So this is velocity and this is time. They now said it starts from a stationary position, a position at which this thing is 0 meters per second, right? So this is velocity in meters per second. Position at which is 0 meters per second. Now it now moves at an acceleration till it attains a velocity of 6 meters per second. 6 meters per second. Now, when it reaches 6 meters per second in a range of what? Of 30 seconds. Right? Now, when it reaches this place, we can now calculate the what? We can calculate the acceleration to be what we have here, which is 0.2 meters per second. Now say a brake is applied, right? A brake is now applied so that it comes down. Sorry, it did not reach 0, but it reaches what? It reaches somewhere around what? Around 4 meters per second. Can you see that it decelerates, right, in the next 5 seconds? So if you check this one now, it is what? It is 35 seconds. So the change in the so if we say we have initial time and we have the final time, so the final time equals to 35, the initial time equals to 30. 35 minus 30 is going to give us 5 seconds, and that's how we have that. And we have come to the end of this video. In the next video, we'll be talking about the graphical representation of motion. We'll be talking about distance time graph and velocity time graph. And as always, subscribe for more content like this. Thank you.